Okay, so we are going to show some example problems on how we can look at the coefficients and the roots and put different things together to answer questions about quadratics. So the first question is to ask us to write the polynomial where x is going to be 4/3 and -7. So what we can do is that if we know that these two things are true, we can say very simply that if x equals 4/3 is a root for our equation, then we would have x minus 4/3. Pretty easy. Now, as one root. And if x equals -7, then that would make x plus 7 one of our roots. Because each of these can be plugged in to our equation to make this whole statement true. Well, we don't stop there. We have to actually go through and multiply everything out, which you may be a little scared of because we have this fraction here, but we can get rid of that. We can get rid of this fraction because we made this statement that it equals 0. We can upscale it to make it work. So to get rid of this fraction, this over 3, we can multiply by 3. So this is the same statement, whether or not we multiply by 3 on both sides or not. Well, if we do that, this right here becomes 3x minus 4. And this over here is just still x plus 7. When we multiply, we only simplify to one term. If you would have multiplied to here and to here, that's kind of like multiplying by 9, because we're not really distributing. We're only distributing into one of these. We're not distributing to both. Now the other side of our equation, 3 times 0, is just 0. So from here we want to FOIL. So we're going to get 3x squared then we get the outside, which is 3x times 7, so that makes 21x. And then have the inside, which is -4 times x, which is minus 4x. And then our last term is going to be -28. And so after we go through and simplify everything, we should end up with 3x squared plus 17x, and we get that from putting these two terms together, minus 28 equals 0. Okay, so earlier we looked at some properties of our roots and said, okay, well, what do we know about the sum and product of our roots just given the equation? Okay, well, we looked earlier that the sum of our roots is the same thing as -b over a. So in this sense, b is -10. So we have -10 over a, which is 5. So this is 2. So quite simply, negative times -10 is +10 over 5, gives us that. So we know that has to be true based off of the property in the concept video that we did earlier. Now a times b, we know that to be c over a. So c is 3, a is 5, and boom, we have 3/5. So these two things are guaranteed to be true based off of the quadratic formula and just kind of playing around with that. Now we can use these properties in order to find other pieces of information. So we're going to use a plus b and a times b later on. So what if we're looking at a squared plus b squared? Well, we don't know what a is, and we don't know what b is. What we do know are the following things. We know that a plus b is 2, and we know that a times b is 3/5. So how do we put all of this together? Well, what if I told you that we could say, well, what is a plus b squared? What is that? Well, a plus b squared, if we FOILed, would be a squared plus 2ab plus b squared. See how similar these are? So, in order to find a squared plus b squared, what we can do is we can say, well, that's the same thing as a plus b, quantity squared, minus this part, right? Because then we're just left with our a squared plus b squared. So we're going to subtract away 2ab. So this, even though we don't specifically know what a or b are, knowing that a plus b and knowing that a times b are certain things allow us to go ahead and solve. Well, a plus b is 2. So this becomes 2 squared. So we're up here. And then we're subtracting away 2 times a times b, which is 3/5. To simplify this, we get 4 minus 6 over 5, which, if you want to think of this as 4 over 1, we can use our little standard kind of algorithm here, where we multiply down. So 4 times 5 is 20. We subtract 1 times 6, which is 6, over 1 times 5, which is 5. So we end up with 14/5. So this is just a problem that exists, and we're using a lot of algebra in order to find this, but it's based off of true statements that we know about our roots. If we wanted to know what our roots squared up and added together would be, we could figure this out without actually going through and finding out what those roots are. We can just use the properties of quadratic equations. Now, what if I wanted to know the quotients and the reciprocals of the quotients added together? So the first root over the second root plus the second root over the first root. How do I figure this out? Well, I need to figure out what this is going to make together. Well, again, using our little standard algorithm here for adding fractions, we do a times a, which is a squared. We then add, the multiplying up, which is b squared. We then divide by b times a, which that is the same thing as a times b. So I'm just going to make that a little simpler. Well, we did find what a squared plus b squared was from our previous slide. A squared plus b squared was 14/5. So here we can get 14/5 over a times b, which a times b was 3/5. Now, anytime you divide by a fraction, it's the same thing as multiplying by the reciprocal of the same fraction. So this is 14/5 times 5 over 3. Now, multiplying fractions is great because you can multiply straight across. I mean, you could go ahead and do this, and that would give you 70 over 15, which is the same thing as 14 over 3. Or we could back up and see, hey, well, if this is really one big fraction, if I'm multiplying by 5 on top and bottom, I can just get rid of that and see that this is just 14/5. So even though we don't know what a over b is and what b over a is, we can use what we know about algebra in order to break it down into things that we do know. And last concept that we're going to talk about here is, let's say we're given that we know that 5 minus the square root of 3 is a root for our quadratic equation. So what would the other one be? So if I know that this is 1, the way that quadratics work is that they always have some center, an axis of symmetry. So this is, excuse me, our axis of symmetry. Our axis of symmetry is always negative b over 2a. And then we have our kind of quadratic going left, and a quadratic going right. And we have some sort of 0 line here. Well, we go to the right and we go to the left. Square root of b squared minus 4ac over 2a. Each direction. Well, one way we subtract, one way we add, and you end up with these answers. Well, anytime you have a form or a root, so if we have the root 5 minus the square root of 3, I'm going to write this like this, 5 minus the square root of 3, going that way. So the difference between these two terms is the square root of 3. If we go the same distance to the other side, we would have 5 plus the square root of 3. So this is the other solution to this problem, because we know that it's going to be symmetric. So if we had 5 and we take the square root of 3 away, we're going to have 5 plus the square root of 3 on the other side. That's just the way that that's going to work. So if you ever run into a situation, and this, if we know one root and it's in this form, we can find the other one just like that every time. Whatever the second term is, whatever the term that's being subtracted or added away, especially one that has a square root in it, you just do the opposite to find the other one. So it's kind of like it's complex conjugate in a sense. That's what they call these.